Hello everyone, and welcome back to the channel. Today, we're digging deep into the fascinating world of geochemical exploration. Ever wondered how geologists find valuable mineral deposits hidden beneath our feet? It's not just about luck, it's a science, and a crucial part of that science is understanding geochemistry. We'll explore how experts use the chemistry of the Earth itself to uncover everything from gold deposits to environmental hazards. We'll cover 3 key principles: how to establish a baseline, how to set up a sampling grid, and which soil layers hold the most valuable clues. So, grab your virtual rock hammer and let's get started. First up, what exactly is a baseline in geochemistry? Imagine you're looking for a needle in a haystack. Before you can find the needle, the anomaly, you first need to understand what the haystack, the baseline, is made of. In geological terms, the baseline, or background, is the normal, natural concentration of chemical elements in an area. It's the standard we measure everything against. This concept is vital for 2 major fields. In exploration geochemistry, we're hunting for unusually high concentrations of elements that might signal a mineral deposit. For example, a spike in gold levels compared to the regional background could point to a new mine. But it's not just about finding treasure. In environmental geochemistry, establishing a baseline is critical before any mining project begins. By knowing the natural state of the soil and water, we can monitor for contamination, manage waste rock effectively, and set realistic goals for restoring the land after the mine closes. It's about being responsible stewards of the environment. So, how do geologists determine this all-important baseline? It's not guesswork. It's a rigorous statistical process. The first step is to collect a lot of samples. We're talking hundreds or even thousands of samples of rocks, soils, stream sediments, and even groundwater. This gives us a comprehensive chemical picture of the entire study area. Once we have the data, we turn to statistics. If you plot the concentration of an element from all those samples on a graph, you'll often see a skewed distribution. Most of the values will cluster together in a relatively narrow range. This cluster, the most frequently occurring value, is called the mode. This mode is what we consider the normal background concentration. Now, you might think, why not just take the average, or the mean? The problem with the mean is that it can be heavily skewed by a few unusually high values, which might be the very anomalies we're looking for. The mode gives us a much more reliable picture of what's truly normal for the area. Once we've established our background value, we can define a threshold. The threshold is the upper limit of what we consider a normal concentration. Any sample that has a concentration above this threshold is flagged as possibly anomalous. It's a potential clue, a hotspot that deserves a closer look. Think of it like a doctor looking at your blood test results. There's a normal range for everything, and when a value falls outside that range, it signals that something different is going on. In the past, geologists often assumed the data followed a perfect bell curve or a normal distribution. They would set the threshold at the mean plus 2 or 3 times the standard deviation. But we've learned that nature is rarely that neat. The concentrations of many elements don't follow a simple bell curve. So today, we use more advanced methods. Techniques like the concentration number multifractal model allow us to separate anomalies from the background without making any assumptions about the data's distribution. This gives us a much more accurate and powerful way to pinpoint areas of interest. Now that we understand how to identify an anomaly, let's talk about how we find them in the first place. This brings us to our second principle: grid organization. You can't just wander around randomly taking samples. A systematic approach is key, and this is done using a sampling grid. The size and spacing of this grid depend entirely on the stage of the exploration program. Exploration is a process that zooms in, starting broad and getting progressively more detailed. It begins with the reconnaissance or regional stage. This is grassroots exploration over a massive area, designed to identify entire geochemical provinces that might be promising. Here, the sampling density is very low. For example, when sampling stream sediments, a geologist might take just 1 sample for every 50 or even 200 square kilometers. In areas without good streams, they might use a very widely spaced soil grid, perhaps with points every 2 kilometers along lines that are 500 meters apart. The goal here is to see the big picture and find the right state, not the right street address. After the regional survey highlights a promising area, we move to the district or prospecting stage. Here, the search becomes more systematic as we try to locate specific mineral targets within that broader province. The sampling density naturally increases. We might now be taking stream sediment samples every 1 to 6 square kilometers, and will start incorporating more soil and rock chip samples. We are zeroing in, moving from a bird's eye view to a more detailed map of the neighborhood. Finally, we arrive at the local or detailed exploration stage. The objective here is to precisely outline the size and shape of the mineralization to guide a drilling program. Now, we're on the ground, walking the property. Sampling is done on a very tight grid. We lay out grid lines, called traverses, that might be only 100 to 300 meters apart. Along these lines, we collect samples at very close intervals, maybe every 10 to 50 meters. For example, a follow-up soil survey looking for kimberlites, the host rocks for diamonds, might use a strict 50-meter grid pattern. The key takeaway is that the grid isn't a one-size-fits-all solution. It's a flexible tool that adapts as we get closer and closer to the prize. The optimal sample spacing is one of the most important things figured out during an initial orientation survey, which helps design the most efficient and effective exploration program. So, we've got our grid planned out, and we're ready to collect some soil. But where exactly do you dig? This brings us to our third principle: soil horizon sampling. A soil profile isn't uniform. It's made up of distinct layers or horizons, each with a different chemical composition. The three main horizons we're concerned with are labeled A, B, and C, starting from the top. The A horizon is the topsoil. It's rich in organic material and humus. While it's vital for agriculture, it's generally unsuitable for mineral exploration. Why? Because elements in this layer are often leached out by rainwater, washing away the very clues we're trying to find. So, we dig deeper. Below the A horizon, we find the B horizon. This is a transitional layer where things get interesting. It's a zone of accumulation, often rich in clays and iron oxides that act like sponges, soaking up and concentrating trace elements that have been leached from above. Metals like cobalt and zinc can get trapped here. Because the B horizon is naturally enriched in these elements, it is often the most preferred layer for a soil survey. It can create a stronger, clearer signal of the mineralization hidden below. Going deeper still, we reach the C horizon. This layer is essentially weathered bedrock. It consists of rock fragments in various stages of breaking down. The C horizon is the layer closest to the source of the mineralization, the parent bedrock itself. Its chemical signature is often very similar to the rock underneath it. So, for exploration, samples are almost always taken from the B or C horizons because they provide the most reliable data for detecting anomalies. In practice, a geologist will first use a spade to clear away the top 10 to 20 centimeters of topsoil to avoid any surface contamination. Then, they'll use a hand auger to drill down, perhaps up to a meter deep, to collect a sample from the targeted B or C horizon. But it's not just about digging a hole. A skilled geochemist must also interpret the entire soil profile and the landscape. The way elements move through the soil, both physically and chemically, can create false anomalies or mask real ones. Understanding the geology of the soil itself is crucial to correctly interpret the data and determine if a target is a genuine, in-place discovery worth pursuing. So there you have it, a look into the core principles of geochemical exploration. It's a methodical process that combines geology, chemistry, and statistics to read the story written in the earth. From establishing a baseline to understand what's normal, to designing a systematic grid to search for the abnormal, and finally, to knowing exactly which soil layer holds the key information. Each step is a crucial piece of the puzzle. This science not only leads to the discovery of the minerals that build our modern world, but also gives us the tools to protect our environment during the process. It's a testament to how we can use our knowledge of the planet to both benefit from its resources and be responsible for its health. We hope you found this journey into the Earth's chemistry as exciting as we do. Thanks for watching, and if you enjoyed this video, Don't forget to like, share, and subscribe for more deep dives into the world of geology. We'll see you in the next one.